Hello, everyone. I'm Kovan Pillay, the director of New York Math Circle. I'm very happy to welcome Dripto Debroy to give us our final talk of the summer. This is a departure from our usual kind of talk. Usually we give talks on mathematics, but this one is on computer science. So without further ado, I'll let Dripto introduce himself and tell us a little bit about his connection with New York. Dripto.
Yeah, sure. So my name is Dripto. I was born and raised in New York City. I went to Stuyvesant High School. And then from Stuyvesant, I went to UC Santa Barbara and got my bachelor's in physics. From Santa Barbara, I went to Duke, North Carolina, got my Ph.D. there in physics. And now I'm employed at Google working on quantum computing and sort of part of the quantum AI division here at Google. So I'm in LA right now, and our office is here. Yeah, so the talk I'm gonna give today is a talk on sort of the basics of quantum computing. It'll explain a bit of the physics, but not very much of the actual physics of the hardware, and more focus on sort of the information theory ideas that we that we build quantum computers off of. So I would say quantum computing is a field that is very heavily reliant on linear algebra in terms of math. Like basically quantum is binary linear algebra systems. And how do we build computing systems out of these objects? So that's sort of the mathematical connection. There won't be a ton of equations in these slides, but we will have some that we'll explain sort of throughout the slide. The goal of these slides are to explain the fundamentals, go over a sort of basic quantum algorithm, and sort of understand why it is like quantum algorithms can outperform classical algorithms in certain ways, and then explain what my PhD was on, which is error correction, and sort of explain some of the math there and sort of how the logic of error correcting codes works and how we can use them to build more robust systems. So with that, I'll get started. The talk should only go about 1:15, so we should have time for a lot of questions. But feel free to interrupt in the middle if you have a question, or like at the end of some slides, I'll ask for questions as well. But we should have enough time, so feel free to ask questions if needed. Yeah, with that, let's get started. So the first thing I want to highlight is sort of what quantum computing isn't. So we're in a very trendy field at the moment. I don't know how much of it you guys see, but there are a lot of claims flying around about quantum computers and what they can and cannot do. And oftentimes the claims of what we can do are a bit extreme. So the first thing is that quantum computers will not replace classical ones. You know, the computers that we have in our laptop or in your phone, they are fundamentally different computing objects, and they have different strengths and weaknesses. There are things that quantum computers are much, much better at, but there are also significant downsides. And so for certain algorithms, for certain problems, for example, like texting, it's much better using a classical communication channel than a quantum one. I think some might not be muted. So, but then, yeah. On the other hand, people are very worried about cryptography and sort of how quantum can break certain crypto systems like RSA, which rely on factoring. And this is a thing that quantum computers are better at than classical ones. But in the next 10, 15 years, most likely, we are not going to be building systems large enough to really challenge RSA in appreciable ways, at least not in the next 5, 10. And then lastly, quantum computers do not work by, quote, testing all possibilities at once. They have some aspect of this through superposition, but they're not just getting the benefits by being like, you know, sort of excessively parallel. That's only part of the sort of way that these things work. And then lastly, I have this little headline here, which gives you a sense for the kind of hype that certain, you know, headlines will show about quantum, which we would like to sort of quell in order to keep expectations at a reasonable level. But yeah, so with that, I want to talk about some things that quantum computers can do. So this image is a slight bit out of date, but it's to 2018 over here, as you can see. But what it shows is on 2 axes, number of qubits and gate error, where certain algorithms fall. So number of qubits, are basically the size of our quantum computer, like the amount of information storage units we have on our quantum computer. And then this gate error probability is that when we actually apply operations, when we do things to our qubits to compute, there's some probability of failure. And our failure probabilities are orders of magnitude higher than those in classical systems. As a result, we are significantly limited in the amount of the length of computation we can do, because our gates will fail if we try to push it too much. And so as we increase our performance in terms of gate error probability, and as we increase the size of our systems, we have access to more and more algorithms. So this in 2018. In 2019, Google actually published the first paper where we kind of crossed over this boundary, where a quantum computer was able to do a task that a classical computer could not do in the same amount of time. And so we're kind of slowly marching up this area. But these first problems aren't necessarily super useful. The algorithm we ran in 2019 was a challenging problem for a classical computer, but it was not a problem that we needed in the world already. Certain systems like VQE can be used for chemistry applications. And so these are actually problems that people might be interested in that we could solve. And so generally, quantum computers are very useful for simulating quantum systems. That's why they exist. Quantum systems are very hard to natively describe in a classical way. And so a computer that is based on quantum components can sort of natively talk about quantum systems. So things like chemical simulation, physical simulations, et cetera, are big parts of this sort of space. They can also be used to factor large numbers. So this is sort of like the Shor's algorithm thing you've probably heard of in the past. And then also there's useful for some encryption and communication aspects that I'm not going to really talk about today much. And then in sort of this space, on this plot, there are two sets of points. There are these like individual solid points like here and here, but there also are these shaded ones here. And these crosshatch shaded ones you can see are labeled as FT. So what FT means, it stands for fault tolerance, and it regards error corrections. I'm going to talk about the end of this talk today. And so what error correction is a way that you can trade off your number of qubits and your gate error. So you take a bunch of noisy qubits and you combine them into one less noisy encoded object. And that way you give up some of your qubit count. So you sort of waste some qubits, or some qubits are made redundant, but you improve on gate error. So you can see that like Heisenberg, if done without error correction, is here. And then with error correction, it can be up to here, where you need many more qubits, maybe 100,000 times more qubits, but you can handle gate errors that are significantly higher as well. So this is a trade-off we'll talk about. And in the long run, most people expect in our field, we need to build large error correcting systems and trade off qubit count to improve our gate error probabilities. So we're hoping to move up on this axis quickly so that we can start trading off qubit count for lower error rates. I heard a beep. Was there a question in the chat? I guess not. That's a different chat. All right. So with that, let's start talking about these building blocks. So what are these qubits? Well, so the classical bit, as you know, is a 1 or a 0, and is how all classical computers store information. So if you have a large number, it is stored in binary, and those binary pieces of information are stored in these classical bits, which are generally out voltage as either high or low, or some other sort of system like that. In the quantum setup, what we do is we use quantum bits, known as qubits. And these qubits also store 0 and 1, but they exhibit a few other quantum mechanical phenomena. So specifically, they exhibit superposition and entanglement. And so we can do, I'll explain these terms in the next few slides, but what we can use is we can take advantage of these phenomena to create interference patterns, essentially. And we can, by doing things clever ways and taking advantage of the extra freedom that qubits give us, we can efficiently solve problems that classical computers cannot reach. And that's kind of the payoff, is that these phenomena here are what give us the power of quantum computing. So then on the bottom here is an image from, I believe, a 20 qubit chip that Google created a few years back. But these are what our systems look like. So we work with superconducting qubits. Our qubits are on two-dimensional pieces of metal that are very, very cold. So they go into the superconductivity phase. And by doing that, we create these very sensitive systems that are super fine-tuned and store a single bit of physical information in them. So this is a 2x10 array of them, and we have little communication pathways and such that you can see. Other architectures are built on floating ions that are trapped in space using lasers, or defects within crystals like diamond. So what is a qubit? Well, as I mentioned, it's similar to classical bit, where except classical bit only can be in purely 0 or purely 1. A qubit can be in a wide variety of states based off of 0 and 1. So if you look at this sphere here, which is called a Bloch sphere, imagine it as a sphere with radius 1, and every point on the surface of the sphere is a different valid state a single qubit can occupy. So you could occupy 0 by being at the top of the sphere, or 1 at the bottom, but you can also occupy some intermediate point here. For example, you could have alpha and beta both equal to 1 over root 2, and in that case, you would have a 50-50 superposition. So you could have that state, and every time you measured it, you would have a 50% chance of 0 and a 50% chance of being 1. So this is sort of the idea of superposition, and it would give our quantum bits such a rich landscape. So instead of just having a single integer 0 or 1, we essentially have like 2 angles to store our information, right? And that's obviously a much larger space. So as I said, this leads to superposition, and it means that you can pick these coefficients. Here's the example I gave earlier, and create a state that is a combination of 2 other states. So it's a linear combination of 2 other states. So there is a sort of nitpicky difference here that maybe will not be intuitive, but there's a difference between a classical and a quantum mixture, or a quantum classical randomness. So a classically random state would be where I secretly give you either 0 or 1 each time, but when you have that state, it is purely 0 or purely 1. And then a quantum state is where I give you a state that exists at a 50-50. And so that means that you can do things to that state and maybe convert it somewhere else, and it'll be consistent. It operates like a single object, whereas a classical one will operate as either this object or that object, depending on what I handed you. So if it doesn't make sense, don't worry too much about it, but just try to understand that these quantum random objects are random at a much lower level than just it was 0 or 1, but you didn't know when you got it. They do not have a defined value until they are measured. So this is superposition, and it gives us the ability to create very unique states with a single qubit. And then that sort of is further amplified by entanglement, which is a kind of famous property, I think, in quantum computing. Many people talk about entanglement. Now, entanglement is the statement that you can create quantum states with multiple bits or multiple objects in any form, which are not describable by describing each individual object separately. So in a computing world, this corresponds to, if you have 2 bits, you can either store 0, 1, 0, 0, 1, 0, or 1, 1. However, every one of those states, I can ask the question, what state is the first qubit in, or first bit in, and you have an answer. And then what bit is the second bit in, and you have an answer. And you can separate that state, you can do all sorts of things with it. However, entanglement is the idea that with quantum objects, you can create 2 qubit states that cannot be separated. So if you imagine the state here, 1 over square root of 2, 0, 0 plus 1, 1. What this is a superposition of 2 qubit states. So there's a state 0, 0, where both qubits read 0, and state 1, 1. However, if I gave you only half one of these 2 qubits, if I split this pair in half, it does not have a defined state, because its state is reliant also on the other qubit that you don't have any information about.
Dripto?
So,
excuse me, Dripto. Remy is asking a question. I think you might have answered.
Yeah, for sure.
Can just read it out to you?
Yeah, absolutely.
Would the property of a qubit being able to exist in 2 places at once make its behavior unpredictable?
Yeah, so there is like I would say a big part of the sort of art of designing quantum algorithms is finding ways to intelligently ask questions. So I can answer that question a bit better in like a bunch of slides from now when I explain the algorithm I'm going to show you guys. But there definitely is a chance if you create these crazy superpositions and then run some algorithm and then don't measure it in the right way, like don't look at the data along the right axis, you'll just get random numbers and you won't really understand what you're looking at. And you have to very intelligently pick what direction essentially you look at the data from in order to get a correct answer. So further, imagine I have a state like this, 0 and 1, right? I can measure in the 0, 1 basis, the z basis, which is along this z-axis here, and I will get either an output 0 or an output 1 based off of which state, and the probabilities will be dependent on which state is closer to the one that I'm asking. So if I'm measuring what this qubit here, or this state psi as labeled, it's much closer to 0 than to 1, and so the probability of getting 0 will be higher. If it was on the equator, it would be 50-50. However, I can also measure along other axes. So I could measure along the x-axis, for example, and then, a state over here would have different probabilities of x and of minus x, or plus and minus as they're known. And so what that means is if I had a state right here, and I asked the wrong question, so to speak, and measured the z basis, I would get a 50-50 chance. I would not learn very much about my state other than it's on the equator. However, if I measured along the x basis and the state was sitting right here, I would have a 100% chance of getting one outcome and a 0% chance of getting the other. And that's like the right question to ask in that case. And I would then learn a lot more about my state because I would know exactly where it stands. So yes, the property superposition can cause you to have very confusing outcomes. And you need to make sure that you really understand what's happening in your system and how to intelligently ask a question along the right direction to get good information. So yeah, hopefully that explains something and that it'll make more sense again as we go on further. Yeah, so go back to entanglement. The sort of things, this is a math camp, right? So you guys will probably be interested in this kind of perspective on it. You can think of a bit, like a two-level object, as existing sort of in this Z2 group. But like basically, it's like, there's a 0 and 1. And then you can imagine a second bit coming in, and now you have the total space, these 2 bits, as being this 2-level part in space multiplied by this 2-level space, right? It's a product space of these 2. So it has 4 levels, but really its structure is 2 levels times 2 levels. The quantum case, these 2 qubits combine to create a native 4-level system. So it explores a full 4-dimensional set of spaces, whereas the 2-level version only explains this 2-level space and this 2-level space separately. And so that might be a bit too abstract, but the essential idea is that as you combine bits, they get exponentially more space to look at, or qubits, sorry. So to describe a n qubit system, you need a matrix that is 2 to the n by 2 to the n. So obviously, you have a very large problem storing this information and learning it. And that's why quantum computers are so hard to simulate classically. Whereas on an n-bit system, you'll obviously only need n bits to describe it. So the qubit case is exponentially more rich as you scale the system up. And that's due to the property of entanglement. So then here on the bottom, I have this image. This is from this paper from Science Advances in 2019. It's not a quantum computing paper, but it was one of the first times, if not the first, I believe, where entanglement was actually like imaged in the lab. So what they did was they prepared a state like this one, sort of like a photonic version of this state, 0, 0 plus 1, 1. But I guess maybe a better way to think about it would be 0, 1 plus 1, 0. So the 2 qubits, or the 2 quantum objects, were both in opposite setups. And what they did is they measured it along different axes. And what they found is that whenever they did so, they would always get clouds. So these, you can imagine this as being like the axis they measured it on. And like 0 maybe is here and 1 is here, or vice versa in this sort of abstract way. And what you see is that they always ended up getting pairs of points. So one would be here, the other one would be here every single time. And that was because these qubits were entangled. So the state of the first qubit was, and the second qubit were correlated, right? And so you would always get one hit here and one hit here, or one hit here, one hit here, one here, one here, but you would never get both clicks on one side or the other. And so this is kind of a physical example to verify that entanglement exists. We can image it, we can show it, and like even look at it on a classical projection of this quantum phenomena. So that's just a cool image. It isn't particularly quantum computing related, but it hopefully helps demonstrate a little bit about what entanglement means. So with that, I'm going to move on to some basic operations. So on the right here, I have the block sphere again, this space of all the states. And what operations are, we also call them gates sometimes. I might say a quantum gate. These are things that you can do to your qubits. So in the classical sense, a NOT gate takes a 0 to a 1 and a 1 to a 0. A AND gate takes 2 bits and then outputs 0 if both of them are, or either of them is in 0, and outputs 1 if you've put in the state 1, 1. So these are classical versions. On the quantum case, there's a number of gates to look at, but I'm going to explain a set of 3 types of gates. So the first one is Hadamard, named after a French mathematician. And the Hadamard gate is applied to a single qubit, and it takes the state 0 to the state 0 plus 1, and takes the state 1 to the state 0 minus 1. So essentially, it's a basis transformation between the z basis, or the z-axis, and the x-axis. So you can think of it as a reflection about a certain plane, and what it means physically is it's like sort of flipping the coordinate system that you're looking at this state in. So then you can notice that if you apply it twice, you will actually get the state back. So Hadamard squared is identity. So h on 0 is 0 plus 1. We often will just drop the coefficients if they're equal. And then if you apply h again to 0 plus 1, this 0 becomes 0 plus 1 again, and this 1 becomes 0 minus 1. The 1s cancel out, and you end up getting 0 back. And the same thing works here. So, so h is, if I'm saying it's a reflection, if you reflect an object twice about the exact same plane, you will get the same thing back at the end. So then we have polyrotations. These are pretty simple. They're just rotations of this space about one of these axes. So like a z rotation rotates on the z-axis, and will change the phase of the state, as we call it. An x rotation will rotate 1 to 0 and 0 to 1, and so on. So these are pretty simple. They're just rotations of the sphere. And the last one, the control knot, is may not the most important of them all, but they're all important. But what the C knot does is it's an entanglement gate, right? It creates interactions between multiple qubits. So here I've just labeled the logic it does. So if a C knot gate is applied to 0, 0, it gets out 0, 0. It's applied to 0, 1, it gets out 0, 1. The 1, 0 spits out 1, 1. And if you apply to 1, 1, it spits out 1, 0. So what it does essentially is it is a controlled NOT gate. So the NOT gate flips 0 and 1, as I mentioned. And a controlled NOT means that if the first state is in the state 1, then the second qubit has its state flipped. So it is a conditional operation. If the first state is 1, then the second state is flipped. So 0 goes to 1, 1 goes to 0. If the first state is in 0, nothing happens. And what this is so powerful is because it allows us to create situations where different parts of the superposition do different things. So if you imagine I have 2 states, both in 0, so 2 qubits. And then, so I have a state 0, 0, for example. And then I apply a Hadamard. What? Is there a question? Okay. Yeah, so if I have 0, 0, and then I apply a Hadamard gate to the first bit, I will have 0, 0 plus 1, 0, essentially, right? So the second state is always in 0. The first state is 50-50 in 0 and 1. If I then apply this control knot operation to it, this state will now sort of entangle itself. So the part of the first qubit that is in 0 won't do anything at all, but the part that's in 1 will apply the next gate, or not, to the C0. And sorry, there's some static. Is there a question? Or is there some feedback from something? All right. Yeah, so the state will then become 0, 0 plus 1, 1, that entangled state I showed earlier. And so this gate allows us to create these crazy large entangled objects. And so it's gates like this, these 2-qubit gates, that allow us to build very complex, high dimensional states within our quantum computer. So these are really vital. And we're going to basically just use Hadamard and control knot gates, or Hadamard gates and 2-qubit operations in order to understand algorithms. So that's kind of what I'm going to move to next. We're going to explain a very simple algorithm called the Deutsche algorithm, which was one of the first quantum algorithms developed, one of the simplest as well. And it has a large version and a small version. I'm going to explain the small version right now, and then I'll talk about sort of how these techniques extend to the larger version as well. So first, let's understand the problem in a classical case. Suppose I have a coin in my hand, and it's either a standard coin with one head and one tail, or a trick coin, like a rigged coin, which either tails, tails, or heads, heads. And you might use to, like, scam your friends. Well, your problem, your challenge, is to figure out whether my coin is heads, tails, or heads, heads, tails, tails. So whether it's fair or tricked. And the way you can do that is that I give you a function, f of x, where x is either 0 or 1, basically numbing the two sides of the coin. And f of x, the value of this function, is either 0 or 1, depending if it's heads or tails. So I'm giving you a function that takes the states 0 and 1, or takes the inputs 0 or 1 and outputs 0 or 1. And my question to you is whether f of x is constant, that is 0 and f of 0 and f of 1 are the same, or whether f of x is balanced, as we call it, which means that f of 0 and f of 1 are opposite. So the classical algorithm, if you want to call it that, for this problem is very simple. You first ask what f of 0 is. I tell you. And you say, OK. And then you ask what f of 1 is. I tell you again. And what you do is you check to do what we said the first time, match what we said the second time. And if they agree, it's a trick coin. If they don't, it's a balanced coin. Very simple algorithm, right? Very simple toy problem. But note there are two queries to your function. You have to ask me two questions. If you ask me just one, you have basically no information about whether it's trick or standard. You need to ask about both sides. So the quantum case is very closely related to this classical version. Someone has a coin, and you're told it's either a standard coin or a trick coin. However, instead of just giving you a function and you ask them directly, they give you what we call a black box. So a black box is some object that takes in inputs and gives out outputs, and you don't really understand the exact inner workings of it. So basically, instead of me looking at the coin, the black box is the coin or is me or something of that nature. So what you do is you input two states, x and y. So x can be 0, 1, some superposition, whatever, any quantum state. So anything on that two-dimensional sphere, sphere. And then y can be also anything on that sphere. And what it outputs is x stays as x, and y is it comes out as y o plus f of x. So o plus is addition modulo 2. So this is just addition in a binary space. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 0 is 1, and 1 plus 1 is 0 again, right? So everything is mod 2. And so instead of giving you just the answer f of x, it gives it to you in this sort of special way, where it essentially encodes that information onto a state you initially gave me. So as an example, if I give you the state y equal to 0, so I put in 1, 0, I will get out 1, and then I will get out 0 plus f of 1. And because 0 plus something is still the thing back again, this will basically give me 1 f of 1. So if I want to do it the classical way, I could feed in 0, 0, and 0, 1, and I would have f of 0 and f of 1 laid out for me, and I could make a decision. However, on a quantum computer, there's a cleverer thing you can do. So first I'm going to explain it in words, and I'm going to explain it in math. So what we'll do is we'll compare the state 0 plus 1 and 0 minus 1. We will feed these two states in as x and y. And what we'll do is the black box will essentially act in parallel on all four of the different possible products of this thing, right? So that's this product. These are two individual superposition states. There essentially are four possible products, and it'll act in each of those four separately. And what it'll do in the process of doing that is that because of the very clever input we gave it, it will actually encode the information we want to know in a relative sign between two of the terms in this now four-term sum. And then if we ask a good question, this goes back to the question from before, right? If we measure it in the correct way, we can actually get the answer to our problem in a single measurement. And so what that means is that the classical case took two measurements, and the quantum case is going to take one. So how do we do that? So this is maybe a bit overwhelming at first. I've color-coded it so that the red states always correspond to the first qubit, and the blue states always correspond to the second qubit. And we're just going to follow along and get to the end here. So as I said, we're going to start with state 0 plus 1 and 0 minus 1 to ease in mathematical notation. I've taken out all of the 1 over square root of 2's, but there are factors of 2 floating around, but they're all equal, so we'll ignore them for now. And we start off with the state 0 plus 1 times 0 minus 1, as I mentioned earlier. Now we can distribute this out, and we'll get 0 times 0 minus 1 plus 1 times 0 minus 1. And so the reason I've split it out in this particular way is that if you remember our black box, it looks at the first qubit, and then based off of the first qubit it does something in the second qubit. So I'm grouping them by the value of the first qubit so that the black box is going to treat this thing and this thing exactly the same. And similarly with these two here. So now we pass in our black box. Remember, our black box essentially adds the output to the second qubit. So for the 0 part, it says 0 O plus F of 0 minus 1 O plus F of 0. And for the for the parts of the state where the first qubit is 1, it will do 0 O plus F of 1 minus 1 O plus F of 1. So again, it does the exact same thing to both of these two states. But what does this do, right? So F of 0 can either be 0 or 1, as I mentioned earlier. And so let's look at these two cases, case by case, just on this first state here. If F of 0 is 0, 0 plus 0 is 0, and 1 plus 0 is 0, or 1, sorry. And so you'll go from 0 plus 1 to 0 plus 1, and nothing will change. However, if F of 0 is equal to 1, then you will have 1 plus 0 here, and you'll have 1 plus 1 here, which is equal to 0 because everything is mod 2. And so you'll go from 1 minus 0 to 0 minus, or sorry, you'll go from 0 minus 1 to 1 minus 0. So as you guys know, B minus A is equal to minus 1 times A minus B. And so essentially what's happening, what this whole thing does, is it multiplies one of these terms by minus 1 in the case that F of X is equal to 1. So just let me quickly pause here and ask if there's any questions about what I'm saying there. Everyone's okay? All right. So again, just to reiterate, the effect of all of this is that I have a state 0 minus 1, and I'm adding to each of these two individual kets, as they're called, but you can think of them as like parts of the superposition. I'm adding the same constant. Now, if that constant is equal to 1, it's effectively flipping the two positions, and so there's a minus 1 factor. And if the constant is 0, nothing has changed. So each of these two pairs of terms will pick up a sign if and only if F of X is equal to 1. And so one way you can write that is you can write it as minus 1 to the F of X. If obviously F of X is equal to 0, minus 1 to the F of X is 1. And if F of 0 is 1, then minus 1 to the F of 0 is minus 1, right? So this is just sort of a clever way of wording what I've said right here. that the sign of this particular term is dependent on what the value of f is at that point. So I will get -1 to the f of 0, 0, plus -1 to the f of 1, 1, multiplied again by the state 0, -1. So I've basically just factored all these phases back in to the state of the first qubit. Is there a question? No? All right. Okay, so we have now is we have the same output, say, we had before, but our input, our red qubit, if you will, has these interesting phases in there. And so now let's think about what our question was again. We wanted to know if f of 0 was equal to f of 1. And so what that corresponds to is saying, is this sign equal to this sign or not? Right? And so what we can do is we can measure in a clever basis. So remember I was saying that like on that sphere, if you measured along the z-axis, you would know whether your state looked like 0 or looked like 1. Well, if I measure on the x-basis, I find out whether my state looks like 0 plus 1 or 0 minus 1. So the difference essentially is that x-basis looks at the relative signs between 0 and 1, which is exactly what we want to know here. So what we do is we measure in the x-basis, which again, as I just said, tells you whether your state is 0 plus 1 or 0 minus 1, up to an overall phase. If it tells you the relative phase is plus, that means that f of 0 and f of 1 agree. And if it tells you the relative phase is -1, that means that f of 0 and f of 1 do not agree. So you just need to make one measurement, and if the signs match, the coin was a rigged trick coin. If they don't, the coin was fair. And so by asking a single input to our state and measuring it along the correct basis, we are able to solve the problem in one query. And so this is a very simple algorithm. Obviously, it's only on 2 qubits. The ones that we need to, the ones that we get paid money to make and build systems to do are obviously on many, many, many qubits. But this problem actually can be extended to a large system. So the core thing this problem uses is superposition, right? Creating that unique superposition in the beginning and asking the black box to calculate on this large superposition state is how we got our value. And you can actually extend this. So instead of talking about a coin with 2 sides, you can talk about a multi-sided die with 0 or 1 at each face and 20, 40, 100 faces. And the quantum algorithm always will solve it in a single execution by essentially extending the argument I made to a large system. However, the classical algorithm always will take n over 2 looks. Essentially, the only way to guarantee you know the answer, if you are given a 50-sided die, is to ask for 25 different sides, 26 different sides, and see if they agree. Obviously, if you get a disagreement early, you know they don't. But the correct way to do it is you need to ask at least 26 questions to guarantee an answer. And so this is how a quantum algorithm can actually outperform a classical one, right? The quantum algorithm does it in O of 1. If you've taken computer science, you might have heard of big O notation, which is like how a problem solution scales with the size of the problem. The classical algorithm will always scale linearly. So if you double the size of your problem, you have a twice as hard thing you need to do. In the quantum case, no matter how big you make the problem, it's just one. Just one application will always tell you the answer. However, we get very little extra information in quantum computing. We basically only get the exact thing we were asking about. So in the classical case, if you do the coin, for example, and I tell you you have a heads and I tell you you have a heads again, not only know that you know the coin is rigged, you also know that the coin is rigged towards heads. The quantum algorithm just tells you they match. It does not tell you the specifics. And if you want to know whether it's rigged towards heads or tails, you'll need to measure something again. So that's kind of a mathematical thing, right? Is that like, if I am extracting all my information in one query, I only get one piece of information. 2 measurements has to give you more information than 1. And it does in the way that 2 classical measurements gives you both rigged or not and which direction it's rigged towards, whereas the quantum algorithm asks one thing, so only gets one piece of information out. Is like a way to think about it. And then lastly, so this is sort of a more abstract concept, but much of the time, the effectiveness of quantum computing and quantum algorithms come from looking at the information in different basis or along a different axis and sort of finding unique ways to look at information in a very high dimensional space. So as I was saying, quantum computing is essentially is linear algebra. Like all the algorithms are just linear algebra. And sort of finding out useful ways to think about looking at high dimensional objects. So that's a quantum algorithm. So I guess I want to definitely stop there and make sure that everyone feels comfortable with that. Obviously, if all of it doesn't make sense, I'm going to give I sent the slides in so you guys can look at them. But hopefully on like an intuitive level, does that make sense to everyone? Okay, I guess I'll move on then. So the last thing I'm going to talk about is quantum error correction. So it sounds kind of fancy. This is actually what my PhD was on. It's more specifically than the rest of the stuff I'm talking about today. But essentially, the idea of quantum error correction, or error correction in general, is making reliable systems from noisy parts. So this happens with the classical and the quantum side. I'm actually going to explain things first through the classical lens, and at the end, I will just last minute extend this to quantum. And that's because the classical case is much easier to understand and a lot easier to work through, like rigorously. So first, let's talk about what the motivation is. Well, in both classical and quantum worlds, there is noise. You know, our systems are not perfect. The classical systems are a lot closer, so they mostly fail when you send a message. I mean, when you call someone on your cell phone and you're using your Bluetooth, your Wi-Fi, you know, we have a rover on Mars sending 4K video back to Earth. Those are not perfect communication lines. Like, we should not have any reason to expect that if the Mars rover sends out, 0010 or something, that we get the exact right bit string every time. And so to deal with this, classical networks use classical error correcting codes to encode their information robustly. However, classical computers are pretty good once they're just sitting there. Like this laptop I'm using will probably get 1 + 1 correct every single time if I run it until I die. Whereas a quantum computer, just existing, can break them. They are degrading constantly. And so we need to much more actively error correct them at all times, not just when you are communicating between different systems. And then as a sort of sense of what we need to get to, Shor's algorithm, which is the famous factoring algorithm in quantum, requires error rates of on the order of 10 to the -10. So if you apply 10 to the 10 operations, only one of them should fail, really. While modern experiments, we can get fidelities, so like failure rates, around 10 to the -2, so 1 in 100 failures. Now, experimentalists are making systems better at all times, and these numbers will go down and down, and they'll get better and better. However, 8 orders of magnitude is probably a bit much for us to ask. These are very sensitive systems, as I mentioned. So how do we bridge the remaining gap? Well, error correction allows us to improve error rates by storing information redundantly. So we use multiple qubits, or bits, to store 1 bit of information in a more robust, protected way. And this, as I mentioned earlier, allows us to trade qubit count for gate error rate. And maybe by creating a very large system in size, we can accommodate slightly for the fact that our operations aren't as good as we would have hoped. So first, let's talk about the classical case that I mentioned. Classical information is stored as 0s and 1s. So the primary error you can think about then is a bit flip. 0 goes to 1, 1 goes to 0. So when you pass a classical message through a noisy channel, let's say there's some probability p that every individual bit gets flipped. So I want to send the message 010, 110, but my friend gets the message 0101, 00. So this second to last bit here has been flipped. And we want to prevent this. We want to have the exact message I want to transmit get through. The way we do this is using an error correcting code. So the code I'm going to talk about is called the repetition code. And I'll go through this sort of thing up top and more carefully. But essentially, it is a code that takes 2 bits of information and encodes them into the storage of 6 bits. So I will send 6 bits of information to my friend, but they will only be able to get 2 bits of information out of it. The rest of it is just to protect it. And the way we do this is we're going to store things in redundant ways. So the 3-bit repetition code encodes the state 0 into 0, 0, 0, and 1 into 1, 1, 1. Now, obviously, if each of these individual qubits fails, you might end up with any of these states in the middle as well as these perfect states in the ends. However, there's sort of this dotted line I've drawn here. And on one side, things are a bit closer than the other. So if I receive the state, or if my friend receives the state 1, 0, 0, they can think, okay, well, either he meant to send 0, 0, 0, and the first bit failed, or he meant to send 1, 1, 1, and 2 of the bits failed, either taking this red or this green pathway. Now, if we assume a little bit of a generous thing, which is that our system is not so bad that it fails more than it doesn't, well, then you are more confident that the first option happened, this blue pathway, than the red or green pathway. And so what you do is you decode, as we say, you basically assume that 1, 0, 0 was meant to be 0, 0, 0, and you correct that to a 0 state. So if a single failure occurred, you're still protected. And this is a way to make your systems more robust. Now, of course, you can increase that level of repetition. So instead of doing 0, 0, 0, and 1, 1, 1, you can do 0, 0, 0, 0, 0, 0, 0, or 1, 1, 1, 1, 1, 1, 1. And you can go higher than that even. And as you make your thing more and more redundant, you'll be more and more robust to error. So the reason why it's very simple, right? You have more chances to fail and still figure out what happened. So here I've drawn some curves where on the bottom I have physical error rate, so the probability of your channel failing. And on the y-axis, I have this thing I call the logical X error rate, which is essentially the chance that your friend decodes the wrong message. And as long as we are below half, the darker curves, which have larger repetition counts, are more protected. So if I have just the n equals 3 case, which is the one I showed you, I'm doing some improvement, like an unprotected qubit would be on the y equals x axis, but you're still, pretty close. You're not helping a ton. However, if I repeat it 13 times, then even if my physical channel fails a quarter of the time, I'm still at probably like a 2 or 3% error rate on the output. So that's pretty good, right? And so scaling these systems up allow us to accommodate for bad errors. So hopefully this makes sense. I mean, the repetition code case is pretty straightforward, but just to really go through it again, I want to explain all of these stages. So I start with a message I want to send, 0, 1. And what I've done is I've underlined the bits that correspond to the first bit of information, and I've not underlined the second bit. So you can kind of figure out what's happening. First, we encode our state. So 0, I call 0, 0, 0, and 1, I call 1, 1, 1. Then I communicate with my friend. So I send this message, which is now 6 bits, to my friend through this noisy channel, whether it's Wi-Fi, text, whatever. And they receive a message that has been slightly damaged. They've gotten 0, 1, 0, 1, 1, 1 instead. However, on their end, they then look at the information they got, think about the code that I told them I used, and then they can now decode that message and say, okay, chances are he meant to send 0, 0, 0, and 1, 1, 1. And so he probably meant to send the message 0, 1 at the end. And so they reverse the encoding, and they can get their outcome at the end. So this is how classical code works. Obviously, the repetition code is very simple. There are more intelligent, smart ways to do it, where you can encode a large number of bits of information sort of in these really abstract ways. Cell phones like 5G using called punctured polar code, I believe. But there are all these fancier versions of this, but this is more only what classical architecture is about. However, there are some problems when you communicate when you bring it to the quantum case. So the big difference is that you can't measure quantum states. You've probably heard this in the past. If you measure a quantum state, you damage it, you collapse it. So what this means is that we need to find a way of identifying the errors without ever measuring the qubits that we're storing our information on directly.
Oh, Dripto, we have a question. Yeah. We have a question from Joseph. He asks, if a quantum computer makes an error in factoring a number, what would that look like?
So what it would look like, I mean, it depends, of course, on where the error is, but essentially, when the factoring algorithm is an algorithm that, so let me explain a simpler case first, and I'll get to factoring. A simpler case in like a chemical simulation, where we actually are natively describing a chemical state on a physical state. So, you know, if you have all zeros, that might correspond to a specific configuration of a molecule. And if you have a 1 over here, that may be a different configuration. So what an error would look like there is that you would be trying to maybe, let's say, evolve a state and learn how a certain molecule would handle some certain situation, and your output would be incorrect. So you would think that the wrong thing might happen. So that's much more of a physical setup. For factoring, depending on which part of the algorithm fails, essentially the core quantum part of the factoring algorithm is a way to take a bad guess for a factor of a number and turn it into a much better guess for the factor of a number. And there are actually really good videos online that explain this in a bit more detail than I'll get into. I think Minute Physics is a YouTube channel that has one. But if you look up online, like Shor's algorithm, you'll find more in-depth, like 15-minute, really well described, detailed images of just Shor's algorithm. But essentially, it's a way to make a better guess out of a bad guess, and you would just get a guess that was a suggestion for a guess that's not as good as it should be. Like you would have an incorrect output. And so your output ends up coming out as like a binary number, and you read it out. So maybe one of the zeros would be flipped to a 1 or vice versa. And so you might get a different number out at the end. But yes, essentially think of noise as just like scrambling your output generally. Like input in your output comes out incorrect. If your noise happens very late, it might be very recoverable. If your noise happens very early in your computation, it's going to spread everywhere. It's going to really cause a lot of problems, and your output is essentially just ruined. But yeah. So much to say, Shor's algorithm is designed with no noise in mind. There are other algorithms we work on which can tolerate a lot more noise because they're meant to be run 1,000, 2,000 times. And if a thing fails once or twice, it gets lost in the average. But algorithms like Shor's algorithm are like deterministic in a way. Like there is one input and you should get one output, and you do it once. And so if it fails, you got to do it more than once, which is, of course, not ideal. Okay, hopefully that answers your question. And then, yeah, so as I was saying, you can't measure your states, right? So when I was saying before that repetition code, my friend will then measure 0000101 or whatever, they're measuring the qubits or the bits because they don't care. These are classical bits. You can measure, if you have a state 010 and you measure it, it's still 010. You don't care. And you're communicating. So your friend wants to measure the bits you sent him. That's the point of the whole thing, is that I'm sending my friend something. They want to measure what I sent. In the quantum case, because we're mid-computation, we can't just break all of our information halfway through to check if we broke. Because obviously in that case, we've broken it ourselves. So instead, we end up having to devise ways of measuring these sort of code states without ever actually measuring the bits directly. And the way we do this is using sort of tests called stabilizers. So when I say tests, you can also call them checks. Essentially what they are constraints that are satisfied for both code state 000 and 111, but might not be true or are not both respected for the other 6 states that are possible. And because both the all zeros and the all one state agree with both the tests, they have the same output, you don't actually learn which state you have when you measure these tests. So you don't end up measuring the information directly. And then we can analyze which tests have failed and succeeded, and we can identify what errors occurred. So this is a bit abstract, and this might make it a bit worse, but the way we tend to talk about these objects, these stabilizers, is through images, through diagrams. So here I have the diagram that we would draw for a repetition code for the 000111 repetition code I showed you earlier. So I have 3 circles. These circles represent the qubits. And then I have these 2 orange bars. And these colored bars are essentially what identify the type of stabilizer we're looking at. So what they are here, in this slide deck, I'm using orange to represent what's called Z stabilizer. But essentially, you can think of it as 0 versus 1, right? So what this bar is saying is that it will check if this qubit and this qubit agree, if they have the same state. So if they're both 0, 0, or they're both 1, 1. And then this orange bar will check if this qubit and this qubit agree. And so you're not actually checking whether this is in 0 and this is in 0. You're just saying, is this equal to this? And is this equal to this? And if they are, like so for the state 0, 0, 0, 0 is equal to 0 and 0 is equal to 0, so you're all good. For the state 1, 1, 1, the same is true. And so these are respected. However, for other states, that might not be the case. So to see that, I have drawn out the same diagram as before with all the 8 possible 3-bit strings. However, underneath, I've put these little colored bars. Now, these bars are essentially whether this 2 stabilizers I showed you earlier are respected or violated. So green is respected, green's good, and red means that that state now fails it. What you'll notice is that the 2 states we want, the error-free states, are both green. However, every other state has at least one red thing somewhere telling us that there was an error. And specifically, they match up. So let's say I measured so now like imagine I'm not measuring the states directly. I'm just getting red, green, 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 red, red, or green, red. So let's say I get red, green, right? So that fades out everything else. My output has been red, then green. So what that tells me is that the check that looks at the leftmost qubit and the middle qubit is failing. They no longer agree, like they should agree, but the middle qubit and the right qubit do agree. And so chances are that the left qubit is like the bad apple. That's the one that's failed. And so I would apply an X gate to it and fix it. However, notice that both 1, 0, 0 and 0, 1, 1 have this exact same outcome, right? I have 3 bits, but I'm only looking at 2 pieces of information. So there's some repetition. And what that means that 1, 0, 0 and 0, 1, 1 look the exact same if I'm just measuring stabilizers. I'm just looking at these checks and not at the actual state themselves, which is perfect because if I apply an X gate, if I flip the first qubit, well, I'm going to take 1, 0, 0 to 0, 0, 0, and I'm going to take 0, 1, 1 to 1, 1, 1. So it all works out, right? I pull out just enough information to fix my problem without ever learning which state I'm fixing it to. So I like to sometimes say that like quantum error correction or error correction in general is a way for a computer to like learn about its own issues and fix them without you having to directly go in. So the quantum computer is learning what errors have occurred and fixing them without you as the user having to learn exactly what state you're storing. And this means that weird complex superpositions are never measured and then destroyed. So this is, nice. Hopefully this makes sense. However, there are other problems as well. So, actually, I'll stop here. Does this part make sense to everybody? Is this okay?
There is another question.
Okay.
From Joseph. Why is it not relevant information whether red-green corresponds to 0, 0, 0 or 1, 1, 1?
Well, so I think it's almost, that question I think it's interesting because it's like, it is relevant information in some sense, right? Like obviously it'd be good if you could tell, but it also would be bad if you could tell because then you would end up damaging your information early. So the goal of quantum error correction is to fix the errors and know what the errors are without knowing where you're fixing them to, if that makes sense. And the reason is because we don't want to learn about our information. We want to not measure our qubits. We want to like ignore all of the actual information about our qubit until we're ready to measure it, because us looking at our information breaks it. So the important thing is that red-green tells us what has gone wrong and not what exact state we're in. I'm not sure that exactly answers your question, but hopefully it gets sort of close.
Okay, so he's followed up. So if you observe whether red-green corresponds to 111 or 000, it breaks?
Yeah, so if you measured, if you design your code incorrectly, so to speak, such that certain outcomes correspond to exact states, then when you measure that outcome, you know exactly what happened, and if your information breaks, it collapses. So think about like a quantum algorithm as like us trying to create this superposition, evolve it in very fancy ways, and then like collapse it later in some specific way so we can measure it. And if in the middle you measure your stabilizers and then you bring everything to 1, well, then you don't have the same state anymore, right? So you can't go back out. So your goal is to fix problems without ever knowing exactly what's going on. And this sort of setup is designed so that you exactly learn the maximum amount of information without ever breaking anything scary.
And Gabriel has a very different question.
Okay.
Are quantum computers Turing machines? If not, then do the traditional mathematical rules for computability still apply?
Yeah, so a quantum computer is a reversible computing device. I'm not like a great information theorist, but yeah, so like anything a classical computer can do, a quantum computer can do. It's just noisier, so you shouldn't, but like you could do it, right? Like you can do all classical logic on a reversible classical computer, and a quantum computer can be used as a reversible classical computer. So they are Turing complete. I think computability, is slightly, I think computability on its own, is the same. However, there's a great debate in the sort of the information theory, like complexity theory parts of quantum computing, which I'm not a member of particularly. But I believe that right now, people do not believe that like quantum computers can efficiently solve NP hard problems. That might be untrue though. I would look it up. I'm sure you can you should be able to find other people who have much more intelligent opinions and they've written them down in like digestible ways. But quantum computers are Turing complete at the same level a classical computer is, as long as it's a reversible computation. So hopefully that is somewhat satisfying. And if it's not, looking it up is probably better than having me go into further detail, just out of my own personal shortcomings as an information theorist. But hopefully that's at least somewhat helpful. So with that, I'm just going to finish up this repetition code bit. So as I said, red, green, you don't know exactly what state you're in, but you can correct the error. And then you get the same outcome as if you had done the argument from the classical case where you had the distances, right? So the same thing applies. However, you fix both cases without ever actually learning what happened. Now, the other problem is that the quantum error model is much richer, right? So we have this two-dimensional surface of a sphere as opposed to just a single 0 or 1. So we have the bit flip error from before. We also have a phase error where essentially the relative signs change. So 0 plus 1, for example, might go to 0 minus 1, and that's an error. So in order to deal with this, we have to now apply two types of stabilizers. So we're not just going to have these orange stabilizers. We will have one stabilizer catch orange errors and different stabilizers catch blue errors, or bit flip and phase flip. And we need to find creative ways of tiling things so that both of these get seen. And so the way we do that is through these codes. This is one called the rotated surface code, which is what us at Google particularly are pursuing as our error correction of choice. In this diagram, orange rectangles, and this is lines, but I've made the 2D ones into semicircles now, will catch bit flip errors. So orange shapes catch blue errors, and blue shapes catch orange errors. And specifically, you'll be able to see, as I'll demonstrate in the next little bit right before we end, that you can now catch any single error on any of these 9 qubits by looking at the outcomes of these 8 different checks now. So there's 2 types because there's 2 colors, there's 2 types of errors, and the same rules apply, but we're not going to actually learn any of our information with the actual physical state or the logical state we're using. We will just find out what the physical errors that have occurred are. So hypothetically, let's say that these 2 states I just darkened, or these 2 checks, were the ones that, fired off. So like the 0-3 stabilizer and this 3-4-6-7 stabilizer both have said something went wrong. Well, so there's a few options, right? So the 0-3 stabilizer could be saying something went wrong because something broke on 0, or that thing broke on 3. Similarly, the 3-4-6-7 stabilizer could be seeing an error on 3, 4, 6, or 7, right? So as an example, an error on qubit 0 and an error on qubit 7 would cause this exact situation if it was an error that the orange stabilizers see. However, there's a special qubit, 3 in this case, which would cause both of these situations with just a single error. And so again, we assume that the lowest weight, the most likely thing has happened. And we say that, okay, we think qubit 3 had a blue error on, a bit flip error. So the 0s and 1s got reversed on qubit 3, and that is what's caused both this stabilizer and this stabilizer to fire off. And so this problem solving of converting sort of these stabilizer outcomes into a particular guess for the error is called decoding. It's a really rich field, a lot of mathematical and cool comp sci in it, while still being a purely classical problem essentially. And it's a thing that like is very easy on a 3x3 grid, but we're hoping to do huge codes. And so this problem becomes non-trivial. And then, as I mentioned earlier, we need very, very low error rates. So this is a 3x3 example, but our plan in the long term at Google, we've published our roadmap to the future, and we're planning on trying to do like 10 by 10, 23 by 23, like very large distance codes. So very large grids, and we're being incredibly robust to errors and get to the super low error rates we desire. So with that, I'm going to conclude. So the summary, quantum computers are powerful tools that outperform classical computers on many tasks. And a lot of these applications involve simulation of like chemical systems and quantum systems. So at least the applications that excite me as a physicist are ones where I can like answer physics problems. An example of an exciting one that a lot of us in the field are excited about is nitrogen fixing. So a large percent, like not large, but a significant percent of the world's energy is spent on making fertilizer. And the way we do it as humans involves like super high pressures and temperatures and these big reactors. In mushrooms, the same thing happens somehow, but we're pretty confident mushrooms don't have a reactor in them anywhere, like they're doing it at room temperature. And so we think the way they do it is using a molecule called FOMOCO, but we aren't sure how exactly that molecule works. It's a very complex, large molecule, and simulating it is very difficult because it's so big. However, a quantum computer could simulate FOMOCO in a decade or two. So we are excited about things like that, where understanding a molecule at a more deep level could provide some utility to the world. And that's the kind of problem that excites me personally as a scientist. Factoring large numbers and breaking people's computers is maybe what government agencies are interested in, but it's much, much farther out, and it's not very exciting on a personal level for me. I don't particularly have much interest in it. And likely things can always change before we can get there. So it's more of a mathematical curiosity than anything else. And then lastly, we will need to see significant improvements in quantum computational power before most applications are within reach. So we're not, basically right now we're making very cool devices that are really exciting, but we are not at the state where we are making devices that are really going to start threatening classical computers on real world useful applications for the next few years, despite what some places will say. Our goals are to develop these devices, and hopefully in the next 5, 10, 15 years, we start putting out useful, cool tools. And then here are also some resources. So QIQC, Quantum and Quantum Computing by Nielsen and Schwang, is kind of like the canonical textbook of the field. It doesn't expect any quantum knowledge. It just starts off with linear algebra, teaches you linear algebra, and then goes from there. So if you guys are excited, math undergrads or high schoolers, I think this is a great book to look into maybe. You might not be able to understand all of it, but it should be interesting. A bit higher level is this video series from Umesh Vazirani, who's a professor at Berkeley. He has it's like a large series of video lectures, and it develops from physics all the way to algorithms. And then lastly, our website is on quantumai.google, and we have a bunch of educational things there, as well as some introductory coding problems and things of that nature to get you started on working on algorithms. And this is the last picture of the team before the pandemic, so I'm not in it yet. I didn't work here at the time, but our team exists. We are always happy to welcome people. But yeah. Thanks.
Thank you, Dripto, for your talk. So if you have any questions, please feel free to ask in the chat session, or you can just, they can just speak up, right?
Yeah, for sure.
Okay. Okay, Joseph, you can just ask the question directly.
Okay, so I'm kind of trying to understand what it would look like if there was an error. So I guess, so what we're considering, right, is functions that map states to states. Is that correct?
Mm-hmm.
Okay, so if you have a state and if it's supposed to output a state, like let's say Z, oh, sorry, my dog is barking. If it's like Z0, or I don't know how to exactly write it, in W1 or Z and W are complex numbers, you're saying that the mistake would happen, it would either have like Z and W being messed up, or one of 0 or 1 being switched.
Yeah, so here, let me go to here. So let's say let's say this algorithm was happening, and let's say it was not encoded. So it's just on two physical qubits are storing all this information, right? And maybe at this input step, right before I put it into the black box, a error happens that, let's say, flips the phase of this state. So now instead of putting in 0 plus 1, 0 minus 1, we'll put in 0 plus 1, 0 plus 1, right? What's going to happen then is that all of these minuses will become pluses. And crucially, these minuses will become pluses. So no matter what the output is, we're going to always get 0 plus 1. And so if you had an error that flipped the sign here, it would mean that your algorithm would no longer actually be asking anything at all. It would take the information, just instantly burn it, and wouldn't notice anything. And you would always get this outcome, regardless of what the actual situation was. So to avoid that, you encode it. No, you're good.
So would that error happen? When you say error, is that something that you can control? Does that mean you messed up in making the algorithm? Or is that something that could happen randomly, that you would have to run the algorithm many times to see if it was happening?
Right. Yeah. So errors are caused by physical processes, right? So of course there is something called, so there's two kinds of errors, right? There's control errors, which is we did something slightly wrong. Maybe a pulse was supposed to go for this amount of time, it went for 1 nanosecond too far or too short or something, or whatever. And that's a control error. And essentially it's our fault. And there's also just completely random errors. So these are incredibly sensitive physical systems. If there's for example, this is not the qubit we use, but there is a superconducting qubit that essentially is a piece of metal with two sides and a skinny bit in the middle. And either a pair of electrons are on this side or on this side. So 2 electrons moving over to their side of a small object corresponds to a huge error in our system, right? And 2 electrons can move for any reason at all. I mean, they're not very locked in place, especially not in a superconductor. So these errors are caused by physical processes, and just random noise will degrade our system over time, and we need to continually error correct in order to drag things back to the right spot. So that 0 minus 1 to 0 plus 1 error could be caused by a magnetic field causing a slight fluctuation in an energy level, and that would cause this to happen, for example.
Okay, I think that kind of makes sense. And I guess one more thing is that if you have two complex numbers representing, so two complex numbers represent a state, is that correct? Or
Sort of, yes. So it's two complex numbers, but there's a single constraint, right? So there is this normalization constraint where alpha and beta are both complex, but alpha squared plus beta squared is equal to 1. So that's why it's like the surface of a sphere.
Okay,
right?
so
not the interior as well. So as a result, like you'll basically have 2 degrees of freedom. Like sometimes you write this as like a cosine and a sine, and like you consider there's like 2 angles to a state.
okay, yeah, I think that makes a bit more sense. And actually, yeah, never mind. I don't think I have any more questions.
Okay.
Any other questions? No? Okay, so thank you very much, Dripto, for giving us this talk on a field that we don't normally discuss. And you're very welcome to visit our program again some other time.
For sure. Yeah, sounds good. And then my email is dripto@google. So if you have any other questions later on, feel free to email me. I'm happy to chat. But yeah, okay.
Thank you.
Bye, everyone. Take care.
Thank you.